Okay, in this video we're going to continue to develop some graphical analysis, graphical perspective, some themes that we've encouraged and developed somewhat in the past. And now we're going to do it with Excel. We're going to, you can see here in the screen, we've got the exponential porosity depth relationship that we've talked about before when we talked about differentiating exponential functions. This is the porosity depth relationship. This is its derivative. We know that the original function is multiplied by the derivative of the terms in the exponent. That gives us a minus 1 over lambda. For this exercise, we're going to make things simple initially. And if you'd like, open up Excel and and follow along as I develop this graphical comparison, this comparison between basically what we want to do is compare the slopes that we calculate. We've said that a derivative is a slope, so we'll calculate the slopes, and we'll do that at a really fine interval of 0.1 kilometers, 100 meters. Okay, not that fine. And then we'll compare those calculations to the actual explicit calculation of the derivative. So we're going to use this abbreviated representation of the porosity. We have phi is equal to e to the minus z. So in this case, we'd be assuming that lambda is equal to 1, that phi 0 is equal to 1. Very unrealistic. We'd be floating in a lake somewhere. The derivative then, the derivative of the exponential term, we're just bringing down a minus sign. We repeat the function. The derivative of the exponent gives us a minus 1. So if we look at the layout here, we've got z's, a column of z's. The sample interval is 0.1. And we could extend this down to a depth of 10 kilometers, maybe an unreasonably high depth, which would take us down to cell 102. I'll probably cheat when I go through this and maybe carry it down to 5 kilometers, but just to get the full view. And then we calculate the porosity, in this case just e to the minus z power. The function in Excel is exp, so you'd have an equal exp, and left and right parentheses you'd have a reference to cell A7. This should be cell A8. Over here on the slope we have B7 minus B6, so we're just calculating the difference. This would be like a y2 minus y1 over a delta x. Delta x is constant all the way up and down. It's going to be equal to 0.1 kilometers, and we calculated slope, and here we have, and I've just taken these formula, the formula in the lines above, and I've just copied them in the line below. So A7 should be A6, and this should be B7 minus B6 would be up here, and minus the derivative, basically this expression here, we'd have equals minus exp, the quantity minus A6. We have the minus sign in front of the z. So there are 4 things that we want to do. We want to make a plot of the function to see what it looks like. We want to calculate the slope point by point, calculate the derivative, and we want to compare the slope and the derivative. We've been harping on this, that derivatives are just slopes, so let's compare a calculation of the slopes to a calculation of the derivative. So this page can be referenced for the basic formula and the basic setup. Next, I'd like to do is just actually go through it. So review a few ideas for constructing these plots. Remember that we have a sequence of numbers, and they're separated by a constant interval, one from the next, so 0.1 to 0.2, 0.3. So if we want to rapidly populate this, and like I said, I'm just going to cheat a little bit and go out to 5. Here, let's see. So that takes us out to 5, and so we've rapidly populated a column of z's. These are depths. These would be z's in kilometers. Have units of kilometers. And then the porosity here. Well, the porosity is, as we said back over here, it's just, we're going to simplify it. It's equal to e to the minus z. So over here, in this expression up here, we just have exp minus a3. And this reference is correct. So we're referring to sol a3 when we calculate the porosity at a depth of 1 kilometer. Okay. And then at 0.1 kilometers, 0.2 kilometers, and so on. The slope, having our initial value up here at 0, we're calculating our y2 minus y1 would be 0.1, or our delta z would be 0.1, but we're calculating the difference in porosity between a y2 and a y1. You get that formula. And then the derivative, we're just using this formula here. Got minus e to the minus z. We've plugged that formula in. So to rapidly fill out all this, we've got our formulas in there. We've double checked our formulas. We'll copy them and move them down to the bottom. And so we have everything plotted up, or got the slope, the derivative, porosity, columns all populated. The next thing to do would be to put together a plot. So I'm going to select all 4 of these columns. This is going to be our independent variable. We've got 3 dependent variables, so we'll use the line plot here so we don't have to look at all the dots. We'll come over here on our design layout. We'll get a quick layout here, and for the axis title we'll have depth and in units of kilometers. Over here we'll have actually the phi dz down here in this region of the graph, and up here we'll have porosity. And we could change the intersection point here for this horizontal axis and let the limits go from -1 to 1 and have the axis value intersect at -1, so that we have something that looks like that. Oh, and yes, down here you see this little hook on the end. This last value on the slope just kind of hangs out there, and that's the reason for that is that there is no B53, so I'm just going to delete that value, and that should take care of this plot here. Okay, so we have a nice plot. I could change the limits on the z-axis, or the x-axis here, the depth axis, which is a z-axis. And so the spot here is there's not much daylight between the slope. We said that the slope should be equal to the derivative, right? Okay, well, hey, look at that. The actual explicit computation of the derivative and compared to that of the slope, which is calculated at 100 meter intervals between points separated by 100 meters, actually lay almost right on top of each other. So we've got porosity up here, and we can see that the only thing we've really done is flip the sign here. We haven't scaled it. So we can feel pretty comfortable in saying that the derivative does provide us at greater accuracy than the slope depicts the derivative at much greater precise. It's much more precise value. So this plot here is informative in that sense, and then also in the sense that even for calculation at intervals of 0.1 kilometers or 100 meters, we do a pretty good job. Okay, over here I've plugged in some different values, and you can see what the effect of changing lambda is going to be. It's a scalar. We make lambda larger. We make this derivative smaller. We make it smaller. Then this becomes larger. In fact, the two are equal when we put 1 in there. If we have 1.5, so we started there. The idea is that at a depth of 1.5 kilometers, the porosity drops off to about 0.368 of its value at the surface, or at z equals 0. So this parameter really controls the rate of drop-off here, and it also scales the derivative. But again, we see calculation at 0.1 100 meter intervals. We see a really good correspondence between the slope and the derivative, very little daylight between the two. And also, well, let me back up here and put this 2 back in. Also, we see that we have a constant error between the two. If we look at the error in terms of a percent, or as a fraction rather, fractional difference, that fractional difference is constant all the way out to 10 kilometers in this case. So that pretty much illustrates and provides a good example, kind of graphical illustration of the similarity between the derivative and the slope. And if you're still having trouble relating to the ideas of the derivative, just think of it as the slope at any arbitrary point on the function that you're differentiating. So the slope at 2 kilometer depths is going to be minus 0.09, just rounding off there. So if we were to draw a line tangent to the curve at 2 kilometers depth, it would have a slope equal to minus 0.09. So I hope that helps kind of drive home this idea as we're developing all these rules for differentiating and so on. It's a good time to kind of come back to the basic, the underlying concept here, that what we've come up with is a nice shorthand approach for explicit computation of the slope without having to go in and take the difference in the porosities between this point and this point, and the difference in the depths between this point and this point, calculate the slope, and then move to the next point. We can do it all in one fell swoop. So hope that helps, and we'll talk to you next time.